Hello students, this is my third lecture on Mossbauer spectroscopy, and in this lecture I am going to discuss applications, and as a first example of this Mossbauer spectrum Mossbauer spectrum is given over here is the FeSO4.7H2O, which you can see. It is a crystal, it is a compound which is commonly used in laboratories, and as a students of coordination chemistry, you will be knowing that it has a structure in which Fe atom lies at the center of the octahedron, and the water molecules occupy the uh, positions as shown over here, the corner positions. Okay, so this was the structure that was thought to be, which all the bond lengths and bond angles were equal. This was the consideration. This was the thing. This was the view initially when the X-ray diffraction was performed on this compound. But later on, when Mossbauer spectroscopy was done on this and the spectrum was obtained, it was found that the spectrum contains a doublet. There's two peaks which basically are doublets because it is due to this Fe center only. There is no other Fe center, and there is a network of such centers which make up a whole crystal. So and what we can see here, there is a isomer shift del represented as over here, and the second thing is the splitting. This is quadrupole splitting. So this presence of quadrupole splitting led to rethinking, and it was indication that definitely this structure is something wrong with this structure. All the bond angles and bond lengths may not be equal, and it may not be a perfect octahedron. So let's first analyze this Mossbauer spectrum. Here there are two things which is important. You are seeing this is del, which is shown with symbol del, is the isomer shift, and this isomer shift is given by this this is the s electron density at the nucleus for the absorber, and this is the s electron density at the source. So this so A minus S, the electron that is the you are subtracting the electron density in the absorber nucleus and the source nucleus with that of the source nucleus. So this is one factor, and there is other factor that will affect the isomer shift, that is del R by R, that is the difference in the radii of excited state nucleus and the ground state nucleus. So this factor is going to be constant because we are going to discuss the cases of different compounds of iron in this entire lecture. So, and this was found to be negative, that is the excited state nucleus radius is smaller than the ground state nucleus, and so this factor is negative for all cases where Fe57 nucleus is discussed. So if you are getting a positive isomer shift as over here, that means that this factor this has to be negative. So we are observing, so we can say that from the Mossbauer spectroscopy results that in case of this ferrous compounds, as shown in this particular case, the electron density in A, that is the absorber here is our compound, this one this has a reduced electron density. So this term will be negative, and negative into negative will give you a positive isomer shift. So this is the case. This is one thing. So you have as compared to metallic iron, there is a reduction in s electron density, which is expected because as compared to a metallic iron, there is a change in oxidation state. So 2 plus means there is loss. 2 electrons have been taken away from the Fe atom. So and the 2 electrons which have been taken away, they are from forest electrons, forest orbitals. So forest so there is definitely reduction in the electron density, and which is also shown electron density at the nucleus, not this electron density at the nucleus due to the s orbitals has been due to the 4s orbital has decreased. So this is a particular case, first thing that comes into to our mind. So there is and second thing is that, so in absence of any electric field gradient, you would have obtained a single peak over here, but in reality you are obtaining two peaks, which is splitting of one peak which could have been observed here into two. So this is, we call it as a doublet. Two peaks of equal intensity are obtained. And so this indicates, the second thing indicates that there is an electric field gradient existing at the nucleus. So that electric field gradient, when it interacts with nuclear moment, it gives rise to this kind of splitting pattern. So the presence of the electric field gradient um, gives electric field gradients will tells us that there is a that the octahedral symmetry is not there in the molecule. There is something more to it that we are missing. So if we consider the structure now based on the Mossbauer results, there must be some asymmetry in the structure. So any deviation from cubic symmetry and will give rise to an electric field gradient at the nucleus. So this structure must have something like that in this. So if we analyze carefully, then we find that we can have electrons filled up in the orbitals like that. In the T2G set there are 4 electrons, and there are 2 electrons in the EG set as shown over here. So there is a asymmetric filling over here, you can see, and T2G4 set will give rise to Jahn-Teller distortion. And this you have already learnt in coordination chemistry classes. So in the first, if the situation would have been like this, the electric field gradient would be 0. But as they split into degenerate, as the degeneracy is lifted and the splitting occurs, distortion occurs because of the Jahn-Teller effect. So we have the electric field gradient now is not equal to 0. There is finite electric field gradient, and we obtain so this structure of compressed compressed octahedron with a Jahn-Teller distortion is the true picture, and this will give rise to an overall electric field gradient, which on interaction with the nuclear moment will give rise to so the tetragonal compression in the molecule along z-axis, and dxy orbital lies lowest and it's doubly occupied as shown over here, whereas all other d orbitals are only singly occupied as shown over here. So this kind of arrangement, so the molecules are not totally symmetric as happens in a regular tetrahedron, and along the z-axis there is compression of the bonds. So so from the discussion on the Mossbauer spectrum, we come to this kind of possibility that can happen. And so the structure was determined again carefully. X-ray diffraction was conducted, and the structure was revealed to be indeed it was a distorted octahedron with x, y, z all being different, and all angles are not equal to 90 degree. Sorry, but all angles were equal to the 90 degree. So moving ahead, we come to this the case of the again we are taking a case of Fe2 plus ions, but this time the ligand is cyanide, FeCN6. So in this case, we can clearly see that it is CN6. It is a low spin complex. That means that T2G, the electronic arrangement is T2G6, EZ0, and it is in a perfect cubic environment. A perfect octahedron would be obtained, and in this case you can only observe an isomer shift, as in this case the isomer shift is slightly negative, and there is no splitting, there is no electric field gradient because there is no asymmetry in the molecular structure. There is no electric field gradient at the nucleus, and so there is no quadrupole splitting. Okay, so this is a very, so we get a single peak with a slight shift from the zero velocity line, which or you can say that as compared to the metallic iron, there is slight shift to the in the negative side as shown over here. So this is the case one which we're discussing here. The second case is of that now we just oxidize this part. If Fe is oxidized to Fe3, that is ferricyanide, then one electron is gone from T2G6 to T2G5, and again there is asymmetric filling of the electrons, and this might give rise to a JT distortion, and because of that you get a splitting, quadrupole splitting in case of ferricyanide ion. So there's there's one more thing that we should note, that the isomer shift of the two complexes, ferricyanide and ferrocyanide, is nearly equal. See here, if you draw a line here, it is the isomer shift for both the cases are nearly equal. How will you explain that? So there's the way to explain it is that there's so there are two things that is happening. There's oxidation. Fe2 becomes Fe3 plus. So in case of Fe3 plus, there is loss of there's one electron from the d orbital is taken away. So in that, that is T2G6 to T2G5. That's what we are seeing here. So loss of one electron from the d orbital means that these 3d electrons were able to shield the 3s electrons present at the nucleus, which are present at the which have an electron density at the nucleus. So if one of these d orbitals d electrons are removed, the shielding would decrease. That the decrease in shielding would mean that the 3s electron will now feel a greater force of the nucleus. So in such case there should have been an increase in what? So the s electron density at the nucleus due to 3s orbital particularly should have increased. It should have increased, but if it would have increased, then we should have got a greater shift, isomer shift. But the second factor that we are missing over here is that the degree of pi back bonding. So whenever pi back bonding occurs, there is donation of d electrons into the ligand orbitals. So this is another way to take away the electrons from the metal site to the ligand. So if you take away d electrons from the metal site, then there will be again the shielding would be reduced, and so there will be so if the electrons are taken away from the metal side, the shielding will again be reduced. On the contrary, if the electrons are if the now if you consider, but in the second case what we are seeing here, the ability to form this pi back bond is reduced, because now you have a greater charge on the Fe3, the tendency to donate d electron will be reduced, and so the reduction in the electron density occurring via this mode, pi back bonding, is not happening. So there will be so these are two factors that counteract each other. One is the loss of one electron, one d electron lost completely, that gives rise to reduced shielding of the electron for 3s electron, reduced shielding of the electron. And the second factor is that reduced pi back bonding ability means there are more d electrons on the Fe site. So there are more d electrons on the Fe. So this will increase the d electrons on the Fe site, which will cause shielding of the 3s electrons. So now you understand this point, that there are two factors working in opposite directions. One is trying to increase the electron density of 3s electrons, and then density of 3s electrons at the nucleus. The other one tends to reduce the 3s electron density at the nucleus because of increased uh, d because of the increased d density at the Fe site, because of as the pi back bonding ability has been reduced. Okay, so these two factors. So overall effect is that the second factor, this factor is able to compensate for the change in the number of valence 3d electrons, and that is the effect of oxidation is compensated by the reduction in the pi back bonding ability, and so we get there is no change in the virtually there is no change in the uh, isomer shift of the ferricyanide ion. This third example that we are taking over here is that of Fe2O3, that is alpha Fe2O3 particularly, because Fe2O3 can occur, ferric oxide can occur in various phases, and the phase that we are talking about, alpha phase, which is hematite. So this hematite was the first compound in which all the three types of hyperfine interactions uh, could be seen in the spectrum. So the first, so that is electric monopole interaction resulting from the isomer shift, resulting in the isomer shift. The second, the electrical quadrupole interaction causing the quadrupole splitting, and third, the magnetic dipole interaction. So all these three factors. So because of that, the expected theoretically expected splitting pattern into six peaks, all the six peaks can be seen over here. Very nicely, you can see. So the intensity you can see 3, 2, 1, 1, 2, 3. So this is the ratio of uh, so the sextet, we are getting a sextet over here, and the sextet will have this kind of intensity ratio within the spectrum. And so this was a very so this can be explained by plotting this kind of feature where you show the isomer shift, slightly shift, and then quadrupole splitting. Del E is small. So relatively speaking, if you consider this, then del E is very small in comparison to the this splitting of G factor. This is your magnetic dipoles interaction. So the splitting due to magnetic interactions, magnetic field is much more than the electric field gradient interaction with the nuclear moment. So uh, and this is how we explain the six observation of six lines with a typical values of this combined typical splitting separation between the lines. So all the separation between the lines can also be explained, and the relative. So we come to the conclusion that there is only small splitting due to quadrupole, small quadrupole splitting, but higher magnetic splitting. So so this is if you analyze the structure of Fe2O3 crystal structure, it is a closed packed oxygen lattice with Fe3 plus cations in octahedral sites, and the Fe2O3 is antiferromagnetic. The internal magnetic field is around 1.5 times larger than that in Fe metal, which is happens to be ferromagnetic. And so the isomer shift is obtained is small as 0.38 mm per second inverse. So this isomer shift you can and this quadrupole interaction is weak. Electric field gradient is weak. So plus 0.12 is the shift that we obtained due to EFG interaction, quadrupole splitting, quadrupole interaction, and a very strong magnetic hyperfield interaction. The hyperfine interaction, magnetic hyperfine interaction is the internal electric field that is created is around 515 kilogauss. So this explains the structure of, and now I'm taking you to another different plane altogether. This is the what we are talking about, the Mossbauer spectrometer, which has been, there was NASA has sent a mission and has planned a mission in 2004, and they sent two rovers, uh, Opportunity and Spirit, on the surface to explore Mars. And each of these rovers contained a Mossbauer spectrometer, very typical. This is a miniaturized Mossbauer spectrometer, which is very uncommon. Actually, the Mossbauer setup, if you look at in a laboratory, it's a huge setup filling up the half of the room almost. But here, what we see is a Mossbauer spectrometer, which is uh, why I am telling you this is that it is in the context of this hematite that has been found on the Mars surface using this Mossbauer spectrometer. And moreover, it has also helped us in establishing that there was water present on the on Mars, or maybe present even now. And this we came to all this conclusion because of this presence with the help of the Mossbauer spectrometer. So this is a very crucial instrument, crucial technique uh, in our uh, uh, extraterrestrial explorations. So interplanetary missions are also now are being equipped with Mossbauer spectrometer. So this is something that you must learn very well. So this miniaturized spectrometer that we are talking about was a special effort was taken to make this Mossbauer spectrometer, and the team leader was from this team leader was Professor Gostar Klinghofer from Johannes Gutenberg University, Mainz, Germany, and he was instrumental in getting this setup ready. Miniaturized version of Mossbauer spectrometry prepared for this special type of expedition. And you will be happy to note that he's an inorganic chemist, and we also take note over here that chemists are nowadays moving into instrumentation, making instruments in a big way. You analyze the Nobel Prizes given in chemistry also, you will find that there's a lot of chemists are now making into making new devices and instruments. So this is so coming back to this. So this part. So the spectroscopy. So this is an application in the interplanetary missions of so Mossbauer spectroscopy led to so main objective was to find the presence of water, and Mossbauer spectrometer helped us in a big way. So two NASA missions were sent with Mars exploration rovers, Spirit and Opportunity. Both landed successfully in January 2004, and this is the spectrum that we obtained. So this Mossbauer spectrometer that were installed in those in that rovers, they could find presence of these iron salts, iron compounds on the surface. So this was olivine, pyroxene, so Fe2 plus ferrous and ferric compounds as well. So why these are important? Because these are the compounds which are found in Earth's lava, which finally weathers to form clay and iron oxides in the presence of water. So, this is something that gave us a hope that water could be present, but there's some more features. Uh, this rover also found blue-colored spherules, small particles, which are shown over here, slightly blue color, and which we now they called the NASA called it blueberries. They looked like blueberries, so it was called blueberries berries, spherules, so bluish colored mineral. And this was at the site of Opportunity rover named Opportunity, and they took the spectrum in a different way. This is you can see that you are seeing the peaks in the upward direction. So this is a scattered Mossbauer spectrometer that was used. This is slightly different, but the other features are same. The transitions are the same. So the thing that you observed in Fe2 typical Fe2O3 pattern, in the pattern of typical Fe2O3 hematite, the same pattern was obtained at when the sample was taken and analyzed at the Mars surface. So the rover analyzed it right over there on the surface of Mars, the features that they saw, it saw and analyzed. So it took a area where nothing like this blue shaped thing, blue colored thing was there, analyzed it, so it got something like this. So this is the noise that we are getting, empty thing which is doesn't contain Fe2O3, alpha Fe2O3. And the second one, the red one that you are seeing, is the actual sample that contains, because if you subtract this part you will get exactly the same spectrum as we expect theoretically for alpha Fe2O3. So this is an important observation, because it presents, without oxygen you cannot have formation of this kind of thing there. So oxygen is present definitely, and probably it hinted towards presence of water, because normally in it is the hydroxyl you form, and when you have to form in the laboratory setup, if you make hematite, you make hydroxide which immediately forms oxides. So there was another important observation through by this Mossbauer's by this rover with this help of Mossbauer spectrometer. It found that there was also silicates, Fe3 phases, jarosite. So these are important things, because they found a mineral of this type in which sodium potassium salt of Fe3 SO4 and dot OH6. So this is very crucial. You see here OH6. This cannot happen unless there is water. So this confirms this evidence conclusively proves that water was present, and maybe it is even now it is over there. So this is, in this case, in this mineral, the water is present in the form of hydroxy group. So it is so this is a thing, a mineral which is also found in on Earth, and it is known to grow in wet sulfuric acid and surroundings like volcanic eruptions, and constitutes a signature of the signature of the presence of water on Mars. So this is a very important finding, and it is very helpful. So the Mossbauer, so this is shows the significance of Mossbauer spectroscopy. In that in an you go to an uncharted territory on a different planet, and you can, if you have to find out water, use this Mossbauer spectroscopy. So now we come back to the Earth and see some more interesting features, some more interesting aspects of Mossbauer spectroscopy when as applied to different systems. So here is another system that we are talking about. Prussian, the dyes, the initially one of the initially first few dyes was Prussian Blue. It is very easy to prepare in lab. You mix ferrous, you take ferrocyanide ions in a solution, in aqua solution, and add to it a aqua solution of ferric ions. So ferrocyanide plus ferric ions gives you this kind of blue color, which we call Prussian blue, and it has a very complex structure. However, if you do the other way around, if you take ferricyanide ions as the aqua solution of ferricyanide and mix it with ferrous ions, solution of ferrous ions, again you will get a blue colored solution which will be called Turnbull's blue. So for a long time, for many years, it was recognized by the earlier workers that these two compounds, the Prussian blue and Turnbull's blue, are very different from each other, but different substances, and even it came into the early inorganic textbooks also. But this was Mossbauer spectroscopy was conducted on, when Mossbauer spectroscopy was conducted on these samples, the Prussian blue and as well as Turnbull's blue. It was surprising to see that the two had very, although the method of preparation was different, the reagents that you took were different, the end result probably is the same because they give the same spectrum. They are chemically identical. So this was the conclusion which again led to a rethinking, and a different mechanism was proposed for the formation of the two dyes, Prussian blue and Turnbull blue. So in Prussian blue preparation, typically you have this Fe3 salt added to ferrocyanide, and finally you get this thing. So the Mossbauer spectrum, so it showed Mossbauer spectrum showed uh, two two features were shown. One was due to Fe3 plus ions, which was in high spin, and the Fe3 plus ion was in asymmetric environment. It was showing a quadruple doublet, and which was superimposed with the singlet, which was a very symmetric environment that we saw earlier in case of ferrocyanide. So we expect that to so there will be a singlet plus a doublet, which was superimposed on each other. So this is the kind of spectrum that was obtained. This is shown on the next slide, and let me show the slide first. So this is the thing that we obtained, that was obtained. Prussian blue, Turnbull blue, both give same, right. So this black line shows the actual spectrum that was obtained. Actual spectrum obtained for Turnbull blue, actual spectrum obtained for Prussian blue. And if you can analyze it further, you can say that it is there are Fe3 ions in the high spin, in the particularly in this case, it is likely to show a doublet, splitting. So there are these 2 and 3 numbered peaks are doublets. So this is a deconvolution performed on the spectra. We can do that using origin. And this is another thing, that is this is the singlet that we were talking about due to FELS. So you can see the color coding has been done in this figure. FELS, this blue color, and this pink to red color one. This corresponds to high spin Fe3. So two different methods: ferric added to ferrocyanide, ferrous added to ferricyanide. Both gave the same type of spectrum, and that means the final structure is exactly the same. So the mechanism now proposed based on this Mossbauer study is that it is uh, this is the so this is a so the final, so both compounds are basically same and have Fe3 outside the coordination sphere and Fe2 in the within the coordination sphere, like this. So when Fe2 plus is added to Fe3 ferricyanide, there is a rapid electron exchange between the two, and this, so you are going, so B, the scheme B gives rise to A, again this one. Due to the rapid electron exchange, Fe2 plus is converted into Fe3, and then the reaction, rest of the reaction is same, and the time scale of this exchange is much greater than the uh, time relaxation time of the excited state nucleus, the Fe57 nucleus, the 14.4 keV line. So it is much greater than that, the rate constant. So it is much faster. So it's a very fast reaction. So we again take a look at we got, in case of FeSO4 7H2O dot 7, we got a doublet. Then FeCN6 ferrous ion, we got singlet because of symmetric environment. Here, because of the JT distortion, it was split into two. There was, so in all the cases we are having here we were having positive isomer shift, negative isomer shift slightly here. And now consider if we replace one of these cyanide ions with say NO plus, then again this spectrum it will look like this. It will so a symmetric spectrum, a singlet which was like this, it is this, instead of singlet now you get a doublet as soon as you replace one cyanide with this NO ligand. So So this leads to now the environment is changed. You do not have a symmetric environment around Fe atom, so there will be a electric field gradient, and therefore, so now you can see here there is the spins are changing from s is equal to 2, s is equal to 0, s is equal to 0. Here there is no so there is oxidation here there is no oxidation, only change in ligand, and due to the change in ligand there is slightly change in the there is a little almost negligible change in the isomer shift, but there is a definite quadrupole splitting due to the electric field gradient present in the system. So whenever there is asymmetry kind of thing, you will have an electric field gradient, quadrupole splitting will be observed. Okay, so okay, right. So this is the example in which we have shown just by replaced one of the cyanide by this. So if we can make a so this is we have already discussed this part. So in case of this kind of settings, you will have no electric field gradient, but as soon as they uh, undergo distortion, there will be net electric field gradient which will be greater than 0. Okay, and so similarly if you so in case of going from ferricyanide uh, ferricyanide which if you replace this with um, sorry if you replace the ferrocyanide with sorry this ferros in the if in the ferrocyanide ion you are one of the Cn is replaced with NO plus, then you are getting again this is the kind of thing that you will get. So this is what we were showing over here. There is this is ferrocyanide in which we have replaced it one of the cyanide with NO plus. So in the same setup we will get so this is how the structure will change. It will there will be a distortion and Z compression will be observed, and so this will give rise to splitting of the quadruple splitting. Although the splitting in this case is less, the spectrum will tell you that the splitting, quadruple splitting, in case of this, the separation this is much bigger, much greater as compared to the quadruple splitting in this case. So now we suppose that instead, so we make a series of such ligands. We go on replacing one this X. This is one of the Cn cyanide ions with X, that where X is ligands such as water and ammonia, nitrite, sulfide, carbon monoxide, and NO plus. So if you gradually go on replacing these and follow these values of the isomer shift, what you find here, what you see here is clearly the you will see that there's as you move from if you suppose you are moving from this water to NO plus, there is the d pi p pi, so a tendency to donate electrons through d pi p pi bonding is increased. If this increases, then uh, the shielding due to the d orbitals will decrease. So as you move from water to NO plus, there is greater tendency, gradual increase in the tendency to donate electrons to the ligands. So the d electron density is removed from the Fe iron site, and because of that, these electrons, d electrons, were acting as a shield to the uh, for the 3s orbitals, 3s electrons. So the 3s electrons, so the shielding will be reduced as the d electrons are moved towards ligand through this pi bonding. The shielding caused by the d electrons will be reduced, and there will be increase in the electron density at the nucleus. This r is equal to 0. So this represents the change at the change in the s electron density at the nucleus. So s electron density gradually increases in this direction as you move from water to NO plus. And so as I earlier said, del R by R is negative already. So if you go on, so this is negative, and this is positive, and this is uh, and this factor, this there is an increase in electron density from water to NO plus. So net result would be that there will be positive to, so if you considering that, so net isomer shift is, so from point it was, so in case of water it was, the isomer shift was 0.31, so there is gradual reduction in the isomer shift as you move towards NO plus. Okay, so if this value is positive, the overall thing will be negative, so you are seeing a gradual reduction in the isomer shift value. So this example demonstrates that Mossbauer spectroscopy can help you in characterizing chemical bonds. So you are obtaining, so isn't it surprising that a nucleus gamma ray absorption event which is occurring at the nucleus is giving you information about the bonding pattern, chemical bonds which is formed in which valence bond electrons were involved. So this is a typical very interesting phenomena that is we have discussed just now. This is something that we have already discussed. So NO plus to S2 plus pi acceptor ligand. So this is the tendency, d pi p pi back donation gradually increases as you move from water to NO plus, and so what we obtained here is that increase in the d electron density as you move from NO plus to H2O. Increase in d electron density near the iron side. This results in stronger shielding of s electrons, and so which creates lower s electron density at the nucleus in this case. And this is the reason for the observed phenomena which was shown on previous slide. So keeping in mind that the nuclear factor, so these are the things that we have already discussed. So that's why you are getting reduction on moving from S2O to NO plus. You are getting a negative decrease in the isomer shift values. Next is the also this isomer shift can be also be correlated to the electronegativity pattern, and the best case to study such a pattern would be the halides. So here you can see what has been shown over here in this graph is that y-axis has this isomer shift, and on the x-axis we have plot, and there is Pauling electronegativity scale. So as you can see here, the electronegativity increases from iodine to fluorine, and there is increase in electronegativity, and clearly you see that as the electronegativity increases, the isomer shift also increases. So there is a direct linear relationship we are getting. This is an interesting phenomena, and it requires further explanation in the sense. So what is here, we should emphasize on the role of 4s electrons. 4s electrons, as you know, we are talking about the 4s orbital is empty. As you when you consider formation of Fe2 plus ion, the 4s, you assume that s electrons, 4s electrons are the first that is being ionized, that is taken away. So but let us consider the MO diagram, only the s interaction part. We will consider only the so that is shown over here, the MO diagram for octahedral complexes showing the ligand orbitals, the metal orbitals. So we can see here the direct forest contribution to the charge density at the nucleus. If there is any forest electron present, it will directly contribute to the electron density at the nucleus. That's simple. But in this particular case, the interaction of metal d orbitals and symmetry at so if you carry out this is kind of if you carry out such calculations and make a diagram like this, you will we can from this diagram we can see that S interaction of the metal d orbitals and symmetry adapted ligand orbitals usually yields the measure part to the stability of the bonds. So there the 4s electrons have the symmetry and energy matched by certain ligand orbitals, which is shown here. The s orbitals of the ligand can overlap, and we can have formation of this kind of psi s orbital. Okay, so even if p and d orbitals form the three sets of molecular which are bonding and non-bonding and anti-bonding in nature, the 4s atomic orbital of the metal is empty and it is energetically rather close to the 3D shell and has the appropriate symmetry to interact with the ligand s orbitals. So ligand s orbital and 4s orbital of this metal combine together to form psi s and psi s star. Now, if this orbital is filled over here by the contribution from the after formation of the molecule, as we are considering over here, and some ligands donate some electron to this orbital, in that case there would be a finite 4s electron density at the nucleus. So that is what we are talking about, direct contribution of 4s electrons into to the electron density at the nucleus in such cases. So the linear the orbital that we are forming over here will be a combination of 4s and the suitable sigma orbitals of the ligand group orbitals that you will take. And you can also see here that in different compounds the 1s 2s electron density remains almost the same. It is unaffected by the bonding pattern. You can see here from FeCl4 to gradually moving to ionic halide ions which are more ionic in nature. Then we are moving to the cyanide, which is most covalent. So most ionic to most covalent type of linkages we are seeing over here. And in this, so we can say that by change in the so when the valence electrons are changed, there is this drop in the there is a change in the s electron density due to 4s orbitals. So this is a gradual variation in all these compounds that we are getting, and this is what we are also seeing in this halides ions. If we replace Cl with bromide, iodide, and this, so if some orbital like fluorine is there, instead of chlorine you have fluorine, then it will tend to, and there will be less tendency to donate electrons, and that will, so 4s electron density would be much less as compared to in case of bromide, iodide cases. So this is, so the bonding molecular orbital psi s will have a predominant ligand character and a smaller amount of s character. Okay, so both ligand character and s character will be there. So any increase in this orbital psi s or psi s star will lead to electron density at the nucleus. This is the key point. Thus, any occupation of psi s electrons will cause a small but not negligible contribution of iron 4s electron density at the nucleus. So, based on what we have seen here, that based on the electronegativity, now if we are talking about, so if we go back to that graph again, then we can see that now you can consider that s electron density from 4s particularly 4s electrons will be significantly affected on going from iodine to fluorine, which change in electronegativity. And so if the so what we are seeing, that there is decrease in the forest electron density gradually as we move from FeI I2 to FeF2, and so decrease in so greater is the decrease in the electron density. That means the first term in the equation that we have shown earlier is negative. The delta R by R is also negative. So net result is that you are having a positive isomer shift, a larger positive isomer shift. So this is the so these are the things that we just discussed just now. And so coming back to it, we have seen. So other than this, there is another aspect to it. That was the direct effect of forest contribution. There is also indirect contribution, which is due to the change in the bond length. Iron ligand bond length and coordination number can also change due to change in the forest electron density in the on the Fe site. Ligand coordination causes a compression of the radial distribution of, the 3s and 4s irons. So ligand coordination causes a compression of the radial distribution of the 3s and 4s iron orbitals, and thus alters the electron density at the nucleus. So as there is, because of the change in coordination pattern, if there is change in bond length, the 3s 4s orbitals electron density will also be affected because of the radial distribution will change, and so that may alter the electron density. So this is an aspect which was not considered earlier. So this influence is about 2/3 of the total variation observed at the nucleus, change in the electron density at the nucleus. So the change in bond length, on considering these 4s electrons, we can come to the conclusion that there is another effect, which is indirect effect, and which is responsible for the change in the bond length, that is iron ligand bond length. And this is the 2/3 of the variations of total in the electron density at the nucleus. So the short and highly covalent bonds show more negative isomer shift. Long ionic bonds, they will show a large positive isomer shift. So this is so therefore, for example, low spin compounds have they will have lower isomer shifts than high spin compounds. This is also a generalization that we can say and that we can talk about. Similarly, oxidation, if you are oxidizing ferrous ions to ferric ion, high spin to high spin, ferrous high spin to ferric high spin, this will cause a shorter iron ligand bond lengths, and lower isomer shifts. So also, if there is a stronger sigma acceptor or pi donor interaction, strong sigma acceptor and strong pi donor interaction, uh, this will also reduce the iron ligand bond length and cause lower isomer shift. So now we come to this interesting part of structural determination of carbonyl compounds. And one of the most interesting case possibly is this that of the Fe3CO12, as shown over here. So the X-ray diffraction studies conducted by Ericsson and Fairhull in 1965, it was inconclusive in the sense it was not able to conclude which structure this molecule adopts. So based on their studies, there were three possibilities that was shown, that was proposed, that either this is the one in which all the three iron centers are equivalent. In this case also, all the three iron centers are equivalent, and there is a bridging bond, CO bond over here. These are this open circles represent the CO bonds, and the closed circle represents the Fe atom. So CO and Fe linkage, you can see this is the bridging linkage. But in both these cases, the environment of the surrounding environment of this iron atom will be similar, is exactly the same. And in this part, the third proposal was that this mm, the one of the iron is different, and the two are equivalent. They have similar configuration. So this was so this out. So these were the three structures proposed based on the X-ray diffraction studies. Now, which one is actually true is difficult. It was difficult at that time to say convincingly which one is the real structure. Here, there's fantastic result that Mossbauer spectroscopy could achieve was this, that it resolved this problem, this in initial years, formative years of the studies of this compound. And what we come to know as when Mossbauer's spectrum was taken, when the spectroscopy was conducted, Mossbauer spectroscopy was conducted on these samples, it was found that there were actually the structure was found to be having two different types of resonance signals, a doublet and a singlet. So total 3 lines were observed with an area corresponding to 2:1 for the doublet to singlet. So this is the thing that is possible. This kind of spectrum can only be obtained. This was actually true, and so the first one, the two different type of resonance signals, doublet is obtained because of the quadruples splitting, and the singlet is obtained for the so there are two iron environments that that we can consider. So this is the spectrum that was obtained: one doublet AA splitted by this quadruple splitting, and a singlet. So this is possible only if out of the three structures only these two environments, these two irons in the identical environment, they will give you this kind of splitting pattern. And if this one is also present, which is slightly different environment with no bridging CO linkage, then this is the typical singlet should be observed. So if you so all these three get all these the two things, doublet and singlet, get superimposed in the actual spectrum, and this is what we obtain. So the intensity ratio, doublet to singlet, red to blue ratio is 2:1, as you can see from the spectrum. It is quite evident. So this is how the Mossbauer spectroscopy could resolve the problem, resolve this structure of Mossbauer this Fe3 carbonyl compounds, carbonyl compound Fe3CO12. And so this is so here I am showing some more data for the other spectroscopic data obtained from Mossbauer spectroscopy, which was obtained for other carbonyl compounds, FeCO5, Fe2CO9, Fe3CO12. This is the one that we have just discussed, in which in all these cases the valency is 0, the iron valency is 0, and the isomer shift in this case was very less, 0.04, and singlet, doublet, two things that was obtained, and that they had even when very fine resolution was taken, the singlet that was obtained, the blue line in the previous slide, that was also slightly splitted into two lines. So that but that splitting was very low. the fact, as you can see, 0.13, 1.12 is the doublet, that larger doublet that we saw. So this is the case for FeCO12, Fe3CO12. Similarly, if you can see that carbonyl compounds are known to stabilize the metal in a low valence stage. So in all these cases, the covalent bonding becomes more important. So there is so you can have, so in a zero valence state also you can see CO5 to CO12 minus 2, positive shift is possible. In case of then you have minus 2 with negative isomer shift, no quadruple splitting, and there is also cases this cyclopentadienyl 2 Fe, that is ferrocene, showing a positive isomer shift and a large quadruple splitting, and so on. So this is an interesting case of the low valent compounds. So there, in these all these compounds, there are basically 5 factors that can be that can explain all the results that we have shown in the previous table. So there could be the 5 factors: an increase in the forest participation in the bonding by a donation from the ligands. If there is anything like this, then this will decrease the isomer shift, right? Because a donation from the ligands in the psi that we had already discussed will lead to increase in forest density at the forest electron density at the nucleus, and so we can expect a decrease in the isomer shift based on the previous formula that we have expressed in previous slides. An increase in the effective 3D population by a donation from the ligands. So there could be also a possible donation in the 3D orbitals of the metal. This will also lead to, so when you add more d electrons to the population, electronic population, then that they are going to at the Fe side particularly, then it will increase the shielding, and because of the increased shielding, the s electron density would decrease, and a decrease in s electron density. So there will be a decrease in s electron density will lead to a increase in isomer shift. Remember, negative into negative gives you a positive thing. So we already have delta R by R, which is negative, and a decrease in the s electron density will lead to increase in del value. So an increase in the pi back donation to the ligands, this is another factor to be considered. Wherever you have a case where pi back donation is possible, this will remove some d electrons from the Fe site. So that will reduce the shielding effect, and if the shielding is reduced, that means s electron density will increase. When s electron density increases, that will give you a decrease in isomer shift. Radial expansion of non-bonding electrons as a result of electron correlation. This will so when you have non-bonding electrons, can also electron correlation that will lead to a decrease in del value. Effective radial expansion of the bonding orbital upon molecular orbital formation. So when a molecular orbital formed, we can say that the orbitals expand. We have already seen in the previous classes on coordination chemistry about the Neff-Loxatic effect. So that the cloud expanding term was coined for that. So there's increased expansion of the electron cloud. So we can also say the effective radial expansion of the bonding orbitals upon formation of molecular orbitals, and this will affect the 3D and 4s symmetry types. This will also have an opposing effect on the isomer shift. Another interesting aspect of this application of Mossbauer spectroscopy is the structural determination of bioinorganic compounds. So the first example, earliest example that we can talk about here is that of ferrodoxin, and this is a protein which is plays a important role in redox processes in the body in a living being. And this sample, which was taken from the algae, oxidized forms. So there are two things that was observed. Here you can see that these are the two spectra that was obtained for the ferrodoxin. This is typically what we oxidized form of ferrodoxin looks like. You have iron centers which are connected through tetrahedrally connected to the sulfur atoms in this manner. So initially both the electrons are in same environment, similar environment in this case, and so they have 5 by 2 with the if we if so this uh, these are in Fe3 plus form with 5 unpaired electrons, so the total spin is 5 by 2, and these two electrons, so 5 unpaired electrons, but these two are anti-ferromagnetically coupled to each other. That is, if one of the at this Fe side all the spins are up, then at this side all the spins are down, and in this manner. So if you conduct Mossbauer spectroscopy on this sample, it will give you this kind of result with a uh, because of they are not in a cubic symmetry environment, so there will be quadruple, there will be a EFG, electric field gradient at the nucleus, which will lead to splitting of the peaks. So we get a doublet over here, a doublet. And when this is reduced, when it gains an electron, turns and becomes a ferrous, one of the electrons iron, so this will become uh, S is equal to, so you will have total spin as S equal to 2, the other one remains like this, other side the Fe status is same. So in this case the number of spins is has decreased slightly, as you can see, because of one electron reduction. So in this case, the spectrum, this becomes Fe2 site. This is Fe3 site. Fe2 site gives a greater splitting due to it has a greater quadrupole field, and because of which it shows a big doublet, which are splitted in which the two peaks are split by a large value, large delta EQ. So this is the quadrupole. So quadrupole splitting in case of ferrous is larger as compared to quadrupole splitting in case of ferric side, and so this kind of spectrum is obtained. So this is what was stated over here. These are the 3 points that was made over here. So high spin Fe2 ion is identified by a large quadrupole doublet and a high spin uh, Fe3 ion with a much smaller quadrupole splitting. So these are the pattern that we obtained, and this helped a lot in initial days. The Mossbauer spectroscopy, so to unravel the structure of the molecule and how the process takes place, the reduction electron transfer process takes place within the molecule. So this was very helpful in determining those things. Here we are. There's another interesting feature of bio applications of the Mossbauer spectroscopy is with magnetotactic bacterium. This is a bacteria in which the magnetite nanoparticles are formed, uh, which are of cube shaped and hexagonal shaped magnetite ions, uh, so about 50 to 60 nanometers size are formed, sorry, 40 to 120 nanometer in size, both in hexagonal and cubic shapes, and they help this bacteria to locate, uh, to find a direction. It acts as a geomagnetic compass, natural compass in the for the bacteria, and helps it find its food. So this is the spectrum that was taken from for these samples from the for magnetite samples from the magnetactic bacterium. So magnetite is a typical inverse final structure. If we and based on that, we expect to obtain two sextet, and which I actually obtained two sextet. You can see 1, 2, 3, 4, 5, 6. This corresponding to these two, and the red corresponding to the red lines. This one. So there another sextet. So there is a so we are able to see here the in both the cases, because of that in an Fe3O4 there is ferrous as well as ferric ions involved in the lattice. The oxygen forms the closed path structure in which you have in the various sites, various holes, octahedral and tetrahedral holes are filled with Fe2 plus and Fe3 plus ions. And so accordingly we are getting so there are two types of sites, Fe sites, Fe3 plus, Fe2 plus sites, and each one having a different type of environment. So we are having a splitting of these patterns corresponding to the two. And the one that you see at the center is the precursors, initial Fe3 and Fe2 uh, ions, which are retained in the bacteria before the formation. So this is gives some other feature peaks near the 0, 0 line. So 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 these are the other so these were the middle of the spectrum. It represents a reservoir of Fe3, out of which the bacteria are building. They can build their magnetic particles. So this is so we come to the end of this topic, Mossbauer spectroscopy. I hope you have learned new things, and you need to go through the all the lectures, or you go through the books by Greenwood, and let me know if you have any problems. Okay, goodbye.